This I was planning to go to 3 dimensions. Maybe we should restart after the Diwali break. Give people a chance to come, right? I mean,
if it's from somewhat basics, we can ask juniors to join some second and third years.
Sure. If they would like to, yeah. It would be not seminar style anymore. It would go back to being, yeah. Or we could do 2 dimensions and whatever. Let's see. But fine. So let us complete our discussion of these dions. Okay. So just to remind you, we discussed the one monopole problem in great detail, both in the case of non-supersymmetric theory, where we discussed that there were these collective coordinates for the motion of the monopole as well as motion in this gauge space. Okay, and this gauge space was compact, so effectively we had a moduli space that was R3 times S1. Okay, momentum in the R3 gave us moving monopoles, and momentum in the S1 gave us electric charges. Okay, that helped us build dions just from the collective coordinate method, starting from the monopole solution. Okay, as you remember, and we also discussed how this story played in with supersymmetry. Okay, we understood that in supersymmetric theories there were fermion zero modes in the background of these monopoles. And in particular, we understood that the fermion zero modes, in the case of the n equals 4 theory, we understood that the fermion zero modes generated a effectively a state with 16 a multiplet with 16 states. Okay, exactly the kind of multiplet that we get for the basic field content of the n equals 4 theory. Okay, this was the square of the number of states we got in the n equals 2 theory. The rest of these lectures we just focus on n equals 4. Okay, excellent. Okay, and one way of thinking of these 16 was that we had 8. You remember the way we got it from counting supersymmetries? The theory had 16 supersymmetries. The monopole broke half of them. Okay, so the broken supersymmetries generate the zero modes. So there are 8 broken supersymmetries and therefore 8 fermionic zero modes. Okay, and then we group them up into 4 annihilation and 4 creation, and the 4 creation generates this multiplet, and therefore we have 2 to the power 4, which is 16 states. Okay, now when we add these, we've discussed how we talk about how we can discuss how the monopole, we had this collective coordinate quantum mechanics to describe the motion of monopoles. So far we've talked only about the bosonic collective coordinate thing. But now, of course, we have to also include the fermionic zero modes into the story. And it won't surprise you, of course, that what we will produce is a quantum mechanics which has some supersymmetry, right? So the total number of supercharges that will be preserved will, of course, be 8. Okay. Now, we have in class at the beginning of this course we talked about theories with 1 supercharge and 2 supercharges. Okay. But already when we had this theory with 2 supercharges, okay, we got the statement that the target space had to be a Kähler manifold with a nice Kähler structure, complex manifold with Kähler structure on it. Okay, we're not going to go through the derivation of this statement here, but I'm just going to tell you how this statement generalizes. How the statement generalizes when you have a rational supersymmetry. Okay. When you have additional supersymmetry, when you have 4 supercharges, okay, when we've got 4 supercharges, okay, this already is enough to give you new structure. It's a new kind of mathematical structure that's sometimes called a hyperkähler space. These are the broken supersymmetries. That's right. That's right. Exactly. Okay. And so we have this hyperkähler, the target space. You see, something that's interesting is the following. The fact that we've got additional supersymmetries tells us we've got additional fermions. Okay, so we've got these. It might seem like a statement about the fermions. Okay, but for the whole thing to close up, this goes and back reacts and constrains the bosonic manifold as well. Okay, so even the statement that we had a Kähler manifold with 2 supersymmetries was a statement that in the end constrained the bosonic part of the target space on which our supersymmetry propagated. Even though the supersymmetry may at first be thought of as, you might have thought of supersymmetry as largely concerning the fermions. For the whole thing to close up, for the algebra to close up, we saw this right in class. We needed that the structure, the kinetic term on the manifold came from a Kähler potential. Okay, so here when we have 4 supercharges, okay, here in this situation where we have 4 supercharges.
You said 8 are the broken.
Yes, so I'm telling you what happens even when we have 4. We actually have 8. Even when we have 4 supercharges. Okay, this thing is hyperkähler. Now what does hyperkähler mean? It means something mathematically. Okay, it doesn't matter very much. Basically, instead of having one complex structure, we have a 3-parameter set of complex structures. Okay, and there is an SU2 invariance that rotates among these 3 complex structures. Doesn't matter. What it means at this point doesn't matter very much. What matters is that hyperkähler manifolds are pretty constrained. Your garden variety manifold is not hyperkähler. For the manifold to be hyperkähler is a pretty strong constraint. Okay, so and when we get 8 supercharges in our quantum mechanics, when we have these 8 supercharges, the manifold remains hyperkähler, and as we've seen in the lectures at the beginning of this course, supersymmetric states are harmonic forms on this hyperkähler manifold. Okay. Now, the fact that you can build arbitrary forms on this hyperkähler manifold, you can see as follows. The total number of fermionic zero modes is 8. Okay. Now, of these fermionic zero modes, we can pair them into annihilation and creation. Okay. As we've seen in the earlier part of the course, the annihilation modes, okay, one of these modes act like the D operator. The other act like the D star operator. Okay, and the fact that we've got these four zero modes tell us that we've got a D operator in 4 dimensions. There are 4 D operators. There's a D operator in each of the directions, roughly speaking. Okay, so there is a form, a dx in each of the directions. Let me say this again. You remember that we have the psi bar. So we've got psi bar I and psi I. These are let's say creation, and these are the annihilation. Okay, and we make states by acting with the two-state system built out of psi bar and psi. Okay, now so let's take a state that is annihilated by all psis, by all psi bars. That is psi, the zero occupation number state. Okay, and let's put that in correspondence, one-to-one correspondence with scalars. Now, if you act with a psi bar, that gives you like a dx. Okay, that gives you some dx psi index. Okay?
Psi bar is the creation operator.
What? Psi bar is the creation operator. Yeah, psis are the annihilation operators, and the vacuum is annihilated by all, exactly. The vacuum is annihilated by all the psi bars, all the psis. Now we act with the psi bar, we create one dxi. Okay? The fact that we have 4 psi bars tell us that we can create all the dxis. There are 4 dxis. So states in this theory are arbitrary forms. Just going back for a moment, suppose we were working in the n equals 2 theory. States in this theory would not have been arbitrary forms because there are only 2 psi bars and 2 psis. And in fact, in that situation, what you would have is that these psi bars and psi, there would be one choice of complex structure so that the 2 psi bars are purely holomorphic, let's say. And so there, states in the theory would have been only holomorphic forms. Okay, because we only have D of holomorphic indices in our hands to create these states. So in the n equals, the theory with 4 supercharges, states are in one-to-one correspondence with holomorphic forms. Okay? On the other hand, here in the n equals 4 theory, states are in one-to-one correspondence with all forms.
So is this like having two, let's say 2 x's, but just n equals to 1, or having n equals to 2 but 1 complex? That's
Yeah.
the kind of difference, is it?
Say that again?
You have 2 directions, x1, x2.
Yes.
But you have just n equals to 1 supersymmetry. That can be any manifold, right?
That would be any, but
If you have n equals to 2, then you are constrained to have a
Kähler manifold.
element. In that case, the forms can only be either D or D bar.
The forms could either be, no, but in that case we had as many psis as x's. Let's say take n equals, yes, exactly. We had, in that case, let's see, how did it go? Exactly right. So there we had 2, the bosonic coordinates were 2 because it was 1 complex, and we had 2 fermions. Okay, but because then there is only one kind of D operator. Yeah, one kind of, so it's like that. But in the n equals 4 is more the usual situation, the generic kind of situation. The arbitrary state is an arbitrary form on this line. And of course, it's always true that supersymmetric states are harmonic forms. That was a general thing that we already saw even with 1 supercharge, if you remember. Okay? So the net conclusion is this, that if we are dealing with this quantum mechanics here, the target space of the quantum mechanics has to be hyperkähler, and a supersymmetric state in that quantum system is a harmonic form. Okay? Is this clear? Now, in dealing with one monopole, we didn't need any of this heavy machinery.
Sorry, can
Listen.
you explain counting difference between n equals to 2 and n equals to 2?
N equals 2, okay, so suppose you were in an n equals 2 theory, so that's 8 supercharges. Okay, monopole breaks half of the supersymmetries. So what you have is 4 broken supersymmetries. The 4 broken supersymmetries will be grouped into 2 creation and 2 annihilation.
So dx1, dx2.
dx1, dx2. Okay, those will be, with one choice of complex structure, will be holomorphic quantities.
I see.
Okay, Whereas here we have twice as many broken supersymmetries. So twice as many size. So twice as many creation operators. So as many creation operators is the total number of dimensions of space-time.
Total emission of the target.
Of the target space, yes. Okay? Yeah. And you know, this way of getting it through broken supersymmetries is a good way for one monopole. But really we should be using index theory, because when we have two monopoles, we get twice as many fermionic zero modes. That's clear when the two monopoles are infinitely far away. But index theory ensures that that's true also when you bring them close by. So I've given you the counting for one monopole, but what will always be true for arbitrary number of monopoles is the number of fermionic creation operators equals the number of bosonic dimensions. Okay? Clear? Okay, excellent. Perfect. So in the case of one monopole, we didn't need all this heavy machinery, right? Space-time was R3 times S1. That happens to be hyperkähler, but you know, R3 times S1 is just some orbifold of R4. It's everything you want, right? You know, you don't have to worry too much about it. And the space was so simple, we didn't need this heavy machinery. The reason we brought it up is that it's going to be relevant when we discuss two monopoles. Okay? Everything we've said applies also to the two monopole space. In that case, space is 8-dimensional, 8 real dimensions in bosons. Okay? But now once again there are going to be 8 creation operators for fermions. So 8 dxi's. Most general space will be arbitrary form in this 8-dimensional space. Okay, so now let's think about it a little bit. What can we say in general about the two monopole moduli space? Well, one thing we can say is the following. Clearly, overall translations should act on this system. Overall translations clearly should have be a factor of R3. Okay? Similarly, overall phasings should act on the systems. We'll come back to this point in a minute. Okay? So, you might think that the structure of this space is going to be R3 times S1 times something. Okay? Now, to try to understand the space better, we should think basically in terms of center of mass and relative coordinates. When the two monopoles are far away, we can make the statement precise. Okay, so let's try to do that. So let's define the following. Let's define X, capital X, to be x1 plus x2 divided by 2 when the monopoles are far away. So x1 and x2 have clear meaning because these are far away from each other. And chi to be similarly half of chi1 plus chi2. Chi1 plus chi2. Chi1 and chi2 are the positions on the two different circles of the two monopoles. Right, you remember that the modular space for each monopole was R3 times S1. And similarly, we'll define psi is, let's do x first. X is equal to x1 minus x2 by 2. And psi is equal to chi1 minus chi2 by 2. Okay? So this is sort of like relative position and center of mass position, also relative position on the circle and center of mass position of the circle. Okay. However, in this circle thing, it's a bit awkward to do this chi1 minus chi2. Okay? Why is that? What was the identification in chi1 chi2 space? Okay, in chi1 chi2 space, suppose we put chi1 and chi2. Okay? we were on this lattice, right? The identification of chi1 lay on this lattice, right? So either chi1 goes to chi1 plus 2 pi is an identification, it gives you the same configuration, or chi2 goes to chi2 plus 2 pi gives you the same configuration. Okay? Now, we want to know what does this mean here for these relative and center of mass coordinates. It's easy to see that this is not diagonal anymore. Okay? In order to do that, suppose we do the following. Suppose we do chi1 goes to chi1 plus 2 pi. What does this do to chi and psi? What it does to chi and psi does chi goes to chi plus pi and psi goes to psi plus pi. On the other hand, suppose we do chi1 goes to chi1 plus 2 pi and chi2 goes to chi2 plus 2 pi. That gives us chi goes to chi plus 2 pi and psi goes to psi. Or if we do 2 pi and minus 2 pi, that shifts psi by 2 pi and chi by nothing. So clearly psi and chi are themselves periodic coordinates with periodicity 2 pi individually. However, there is also this cross-linking. Okay?
Because it's a torus.
Exactly. Yeah. So one way of thinking of the identification space in chi plus psi is that each of these are coordinates on which are 2 pi identified, but plus there's one additional identification. That is chi goes to chi plus pi and psi goes to psi plus pi is also an identification. It's not completely decoupled. Okay, it's easy to check that this completely gives it a space of identification. Okay, so this thing here is not quite right. Okay, what we should have is a manifold that looks like R3 times S1 times M4 by Z2, where the Z2 action acts on this S1 like a pi rotation, pi shift, and on M4 with what will look like a pi shift when you go to infinity. So that chi1 and chi2 are well defined. But in general, it's some Z2 action.
Sorry, what is M4?
M4 is the manifold for the center of mass motion. Okay? You remember that what we had was R3 times S1 times something non-trivial. That something non-trivial I'm calling M4. But I'm saying it a little more precisely now, because it's not quite a cross product. Right? You see that when the two monopoles are very far away, that something would also have been an R4. Okay? But it wouldn't have been quite R3 times S1 times R3 times S1 because we've gone to center of mass and more. Okay? It would have been that plus a Z2 action that acts uniformly on both. This pi shift. Is this clear? Okay? Now, on the center of mass part, the Z2 really acts like a pi shift on S1 because that part is free. On the relative coordinate, we're going to get a non-trivial metric in this relative space. Okay?
It acts as pi on chi.
It acts as pi on chi, exactly. A pi shift on chi. Okay? On psi, it will act like a pi shift on psi, except psi will not be thought of as chi1 minus chi2 anymore. This decomposition of psi and chi into chi1 plus chi2 and chi1 minus chi2 is something that is only possible at infinity. Okay? So it will act as a pi shift, or some Z2 action on this non-trivial manifold M4. Okay, and maybe you can choose a coordinate on that manifold which we'll call chi, for which is a pi shift. But it's just some Z2 action on this non-trivial manifold M4. Is this clear? Okay, the Z2 action on the S1 is just literally a pi shift because for the center of mass it remains R3 times S1. But in the relative it's going to be some complicated metric. It's just the abstract way of saying it is just some Z2 action which when you go to infinity reduces to pi shift on R3 times S1. Is this clear? Okay, excellent. So in general, the two monopole moduli space is going to take this form. Question, what is the manifold M4? Okay, now the answer to this question was determined by mathematicians. Okay, by Atiyah and Hitchin, in fact. And let's see what went into that determination. Okay. Firstly, I'm going backwards. Interesting. Firstly, they used the following. They used the fact that this metric was hyperkähler. This gave them some restrictions. Then they used the fact that it had to have an SU2 action on it. That there had to be an SU2 isometry on it. How do we know that there's an SU2 isometry? Well, that's just rotation invariance. Our whole system had rotational invariance in it. So no matter how complicated this two monopole moduli space is, it should admit the action of rotations. You remember how it worked with one monopole moduli space, right? We had to do some linear combination of what we naively thought of as rotations and some gauge transformation, some diagonal action. But in the end, it was a rotational invariant. This should be a general thing, right? Because physically we should be able to perform rotations. Now the R3 automatically has rotations in it. But for this to survive also, you might have thought maybe one way of it working is that it acts only on the R3 and is trivial on the M4. But we know that's not the case. Because when these two monopoles go after infinity, M4 was just x1 minus x2, and this is also rotated. Okay? So there is a non-trivial action of the SU2 on M4 itself. So this M4 has to admit the action of an SU2 symmetry. Okay? And finally, there was one more technical assumption they made, something about completeness. Doesn't matter. I think that in our context is equivalent to saying that A, you know the asymptotic form of the metric to be basically two monopole moduli space, and B, that it should not have any singularities anymore. Okay? Using these things, they were able to completely determine the metric on R4. Okay? So I'm going to tell you a little bit about their answer. The actual computation is complicated. Okay? But I'm going to tell you a little bit about the answer. First, what we've got is some four-dimensional manifold. Right? Now, if you might have thought, that suppose that our answer preserved not SU2 but SO4. Suppose for a moment that was the case. Then what would we have done? Then what we would have done was to say, well, our metric must take the form ds squared is equal to h of r dr squared plus r squared d omega 3 squared. Or maybe some g of r. We have of course had freedom to perform radial field redefinition. Okay, this is the kind of thing we do when we're trying to find a Schwarzschild black hole, for instance. Right? Had it preserved, suppose we were looking for a Euclidean manifold that had preserved a large symmetry, namely SO4. Okay? And that would have come about because we know the isometry group of an S3 is SO4, because one way of understanding that is think of the S3 embedded in R4. Okay? So had we had SO4, which is SU2 times SU2 preserved, this would have been the form of the metric. But we don't have that much. We only have an SU2 preserved. So is there some way of deforming this structure? Is there some way of deforming the structure, okay, to preserve an SU2, one of the two SU2s out of SU2 times SU2, rather than both of them? Now, there is a very beautiful way, which I'm going to tell you about, or maybe some of you know about it. Yeah, do you know about left and right invariant one forms? Yeah, let me tell you about it. Okay. So, one way of thinking goes as follows. One way of working goes as follows. Okay. Suppose we've got an S3, like this one. Okay? And we want to analyze the space of vectors or equivalently of one forms on this S3. Okay? First, actually, first let's do it for scalars as a warm-up. Suppose we want to analyze the space of scalars on this S3. Okay? Scalars on the S3 transform in the following representation of SO4. L being any integer, meaning they're completely symmetric, traceless combinations of the basic SO4 vector. Is this something you're familiar with? That the space of scalar spherical harmonics is labeled by these representations. Is this something you're familiar with?
Just like for SO3 we have.
Yeah, for SO3 it's sort of almost trivial because there the set of all representations was one parameter. So basically all integer representations appeared. Yes. Here the set of representations for SO4 could have two columns. Yeah. But I'm saying only one of them appears. So it's much less trivial. This is something you don't know? Let me tell you about it for a minute. This is, yeah. Let me explain how that works. Okay, so this is an aside on spherical harmonics. Okay? Suppose I want to think of all functions on an S3. Okay? One way of thinking of it goes as follows. You see, functions on an S3 are same as functions on S4 and then restricting to the unit sphere. Sorry, R4. R4 and then restricting to the unit sphere. Now we know basis of one nice expansion basis for functions on R4, which is Taylor expansion. Okay? So every function on R4 can be written as a I1 in x I1 x in. And therefore these coefficient functions A's are a basis set of data for functions on R4. Okay? However, we're not interested in functions on R4. Notice that these A's, by definition, are tensors that are completely symmetric. Okay, so there's a one-to-one correspondence between functions on R4, at least regular functions that have a Taylor expansion, and the symmetric coefficients, symmetric tensors with indices that take values 4-dimensional. I1 to I4 goes from 1 to 4. That's clear, right? However, we're not interested in functions on R4. We're only interested in equivalence classes of functions. Two functions are going to be regarded as the same if they agree on the S3, on the unit sphere. Okay? This tells us that every factor of xi, which is 1 on the unit sphere, should be treated as 1. So we don't want any functions that have in it an a contraction. Because any function involving a contraction is equivalent by our equivalence rules to a function without that contraction. It would be a function with the lower dimensional tensor, but without the contraction. Is this clear? Okay? And therefore, it is sufficient for our purposes to look at guys such that the property, symmetric tensors such that they have no contractions with each other. Symmetric tensors such that you take any two of them and contract them and you get 0. Traceless symmetric tensor. But you know that these representations are precisely traceless symmetric tensors. Okay, let me say it more precisely. That notation is usually used for SUN. So, and the purists among you are feeling uncomfortable. How do you draw Young diagrams for SON? Let me say it a little more precisely. The highest weights, okay, the highest, if we take SO4 and take two planes, imagine R4, break it up into two planes. And let's call H1 and H2 the eigenvalues under rotations in each of the two planes. This is the usual choice of Cartan basis for SO4. Or at least it's usual for SON. SO4 exactly, we can do SU2 times SU2. We come to that. Okay, this is the usual choice of Cartan basis for SO2n at least. Okay, what I mean by this object here is the guy with the guy whose highest weight has H1 equals M and H2 is equal to 0. That symmetrization tells you that because it's symmetrized, you can put all the highest weight vectors into 1, 0. Had you had an anti-symmetrized, you couldn't have. Then that would have been 1 and 1. Okay? So what I really mean by that notation there is this representation. H1 equals M, H2 equals 0. It's clear that traceless symmetric tensors are giving us those. Because by removing the trace, we made it an irreducible representation. And it's clear that we can put all the i's in the highest weight. Remember, the highest weight is complex, so when you put them all in the highest weight, that's consistent with being traceless. Because there's no GZZ component of the matrix. Is this clear? Okay? So, this is the set of representations that give you spherical harmonics. Something to remember is that you do not get all representations from spherical harmonics. You only get a one parameter set of representations rather than a two parameter. Representations is some group theory thing. Spherical harmonics is what happens when you put functions on a sphere. These are two, in principle, different things. The fact that they almost happen to coincide for SO3 is a coincidence. It does not extend to any higher SO. Okay? Now, I've been labeling representations with this H1 and H2, which are these Cartans, these rotations in the two planes. But precisely for SO4, it's sometimes useful to label it under SU2 times SU2. Now let us remember what the relationship, so let's suppose we call, I don't know, J1 and J2 the Cartans of the two SU2s, JZ of the first guy, JZ of the second guy. Okay? What is the relationship between the two? Well, I'll write down something and then I will check it. I believe J1 is equal to H1 plus H2 by 2 and J2 is equal to H1 minus H2 by 2. Let's check. If we take the vector representation, that's H1 equals 1, H2 is equal to 0. But we know that's half-half. So that works. We take a spinor representation. The chiral spinor is H1 equals half, H2 equals half. From here that will become half 0. Antichiral representation, H1 equals half, H2 equals minus half. It will become 0, 1, 0, half. Perfect, right? Okay. So these representations, which were H1 equals M and H2 equals 0, in J1, J2 language become M by 2, M by 2. Just using that formula. So the representations we get from spherical harmonics are those in which J's of the two SU2s are the same. You can't choose some value of J here and some other value of J there. spherical harmonics give us that. Okay? So this is, and actually, this way of thinking of spherical harmonics is far the best way of thinking. For instance, if you want to evaluate the Casimir on a spherical harmonic, let me suggest the method and you can try it as an exercise. You know that if we act with del square on that function here, del square in R4, what we will get is, we've got two dels, del mu. One of the dels will act on one x, another del will act on the other x. We'll contract the indices, but since A is traceless, that will give you 0. So del square of this is 0. But now we can work it out in spherical polar coordinates. This thing is r to the n times some function of angles. And then we can write del square in spherical polar coordinates. So it's d2 by dr squared plus 1 by r squared, d by dr, r squared, d by dr. I said it wrong. Del squared is plus 1 by r squared del S3 squared. Right? This formula with square root g's will tell you that this is the case. Okay? But we know that this thing must give you 0. But we know what this does in acting on the guy with n indices. Because the first guy will give you n, and then the second guy will give you n plus 1. Because you'll reduce by 1, but then add 2. Okay? But you'll get that with 2 powers of r smaller. This guy also reduces by 2 powers of r. And so we get n into n plus 1 plus del S3 squared is equal to 0. And this gives us the formula for the Casimir, for del squared on spherical harmonics. And you can check this is the right answer, I hope it is. But I mean, we'll check if you do it right, it's the right answer. And this generalizes so easily to higher dimensions. Okay, this is way the best way to think of spherical harmonics. So far we've dealt with scalars. Okay, now let us broaden our horizons and deal with vectors. So we want a mu, or one forms, a mu of x. So the first thing we're going to do is to start thinking of these vectors on R4. But now we've got two things that we have to demand. First, that a vector field, the same thing, that if we have, we're only evaluating the vector field on S3, and so any factor of x squared we want to throw away. Okay? But second, we want this one form index, the tangent space index, to be along the S3. Okay? So, if we write this as equal to a mu and then mu1 mu n x mu1 we get two conditions. First condition, that this guy has to be normal to the radial vector. That is, if I multiply by this, I get 0. This is more or less the condition that this index, when completely symmetrized, in fact is the condition that when this index is completely symmetrized with all the others you get 0. On the other hand, if you contract two of these, you should get 0. Contracting two of these means traceless as before. But now we've got a new condition. We've got this A index with one index free, which when symmetrized with the other indices gives 0. That tells you that it's in this representation, right? If we have n of these, then this thing's size will be n. This guy was this index. These guys were all the guys. So vector spherical harmonics, the space, you take a vector field and expand it on. So let's just remind ourselves, what question are we asking? We're asking, suppose I take a vector field and expand it on S3. What, and then act on it with rotations. What representations will appear? And we've got the answer. Okay, now let's take this and put it in language that a mathematician will tolerate. So that was H1 is equal to M and H2 is equal to is equal to 1. Right? That's what this translates to. But now let's try, this is clear. But now let's turn that into J1, J2. J1, J2 tells us we've got M plus 1 by 2 and M minus 1 by 2. Okay? Now, what values can we have for M? Well, clearly, because we've got this box here, we can't have M equals 0. This starts from M is equal to 1. So it's these representations where M is equal to 1, 2, up to infinity. Now let's look at M equals 0. Sorry, M equals 1. That is the representation 1, comma 0. And then we will have 3 halves, comma half, and so on. We'll keep going. But notice 1, comma 0 is interesting. Okay? 1, comma 0 is interesting because that tells you that this particular guy is invariant under one of the two SU2s, but transforms under the other. Okay? Now, I have not been very careful with self-duality here. I pretended that H2 is always less than H1. But because of the self-dual business, that's not always the case, and so on. So when you take care of that, you could switch the two SU2s. Clearly, there's no difference between the two SU2s. It's the SU2. So you've got a set of a three-dimensional space of 1 forms. That is, in the spin 1 representation of one of the two SU2s and spin 0 on the other, and similarly the other way around. The first set of these 1 forms, whatever, these are fields, right, on the sphere. They come by, you can actually obtain them from this procedure. You can obtain the explicit form, if you like, from this procedure. Okay, you take the guy with M equals 1, and so on. Okay? It's not hard at all. In fact, what you have really are the generators of rotation. Anyway, we won't get into all of that in any great detail, but you see, right? Anyway, it doesn't matter. So what we have is the forms that are 1, comma 0. There are also the 0, comma 1. The first kind is called left invariant 1 forms. And the second guy is called right invariant 1 forms. Okay? So for all the 1 form fields in the world, we're not worrying about whether they obey some equation or not. Just under representation. If we decompose it into representation content, we see that there happen to be exactly 3 1 forms that are annihilated by the right moving SU2. And 3 1 forms are annihilated by the left moving SU2. Good. Now, 3 because spin 1. Spin 1 is 3. 3 is a 3-dimensional representation. Okay. Now, so if you are interested in starting from an S3, and which preserves SU2 times SU2, and deforming this metric so that it does not preserve all of the SU2 times SU2, but only preserves one SU2, then you can add to it a bilinear form of the left invariant 1 forms. That will preserve the left SU2, but not necessarily the right SU2.
But wasn't that SU2 isometry some diagonal thing?
Which one? Sorry, say again.
The SU2 isometry that you said for the Kähler.
Well, that was you're talking about the monopole thing, right? That was diagonal between gauge and this. This is a completely separate thing. Now we're just being more abstract. We've got a metric, okay, on R4, and we're trying to preserve some SU2. Okay, and this is mathematically basically the way to do it.
So you can always add these forms if right SU2.
Exactly. So we choose one of the two SU2s, we'll preserve that, we'll add only the, let's say we choose the left SU, we'll add only left invariant one forms. Now, in fact, it's not hard to convince yourself that you can write down the round metric on the sphere. Okay, so let me call you can write down these, in some coordinate system, you can write down explicit expressions for these one forms. They're sometimes called sigma I. I is equal to 1 to 3. Sigma 1, sigma 2, sigma 3. And roughly speaking, sigma 1 squared plus sigma 2 squared plus sigma 3 squared is actually also right invariant. Because sigmas under left were invariant, but under right transform like vectors. But you take this combination, and it's invariant even under right. And that is in fact the round metric on the sphere. Written in terms of left invariant one forms, the round metric on the sphere, which preserves SU2 times SU2, is that.
Casimir is the.
What?
This looks like
It's sort of like the Casimir, but of course this is in terms of forms, so it's not number. Okay, but something you might worry about as well. You've favored left over right, which in politics is a good thing to do, but but okay. What about the symmetry? We could have done it with right invariant one forms. And something you can show is that while in general you get completely different answers, exactly this combination of left invariant one forms equals the same combination for the right invariant one forms. Because the round metric on the sphere is unique. You can show that, for instance, just by working out in some coordinates. Okay, excellent. So that was the round metric. But we are not interested in general in the round metric. We're interested in any metric. Okay, we're interested in any metric that preserves SU2, the left invariant SU2. So any bilinear forms under these SU2s, under these sigmas will do for us. Okay, so this was the principle this was the way that Atiyah and Hitchin started. They wrote down like an ansatz for the metric in terms of these one forms. Okay, that ansatz now is guaranteed to have SU2 isometry. Then they put in all the other conditions that they had. Okay, and when the dust said the other conditions turned into differential equations which they could solve in terms of hypergeometric functions and get just a unique answer.
Other condition is in
Mainly hypercaleness. And some completeness business which I believe is asymptotic behavior as well as no singularities. So these are all local conditions, and then there's some global conditions.
This gives you
Unique solution.
for informative.
Word for M4 metric. Amazing, right? It's so amazing because otherwise this is a very complicated dynamical question. And one that could receive corrections order by order and a coupling constant or something like that. But since the answer is uniquely specified by general constraints, this is the exact answer. Clear? Okay. So the two monopole moduli space is, just exactly known, and is just exactly known, and basically takes the following form. I'm going to write it schematically. Okay, it takes the following form. It is f of r, the whole thing squared, dr squared, plus a of r sigma 1 r. They've done right invariant, not left invariant, okay? Plus b of r sigma 2 r, the whole thing squared, plus c of r squared sigma 3r square. Okay? Most general right invariant structure could have had cross terms, but this is not allowed. It turns out not to be. Actually, very simple considerations rule out the cross terms, but doesn't matter about all of that. Okay? And here there is, of course, one coordinate arbitrariness, because the coordinate r can be redefined. Okay, now there are many possible gauges you could choose for that. A convenient gauge is to make the following choice. B of r by, minus B of r by r. Instead of, we don't really have four unknown functions in the game. We have 3 unknown functions. Okay, so we choose some choice of coordinates to fix what we mean by r. This is something that proves to be convenient. Okay, and then what these guys did was to completely solve for these things. Now the solution is in terms of hypergeometric functions, and I don't know about you, but when somebody writes down a hypergeometric function on the board, I don't take anything from it, so I'm not even going to write it down. Okay, but I'll just tell you a little bit about the answer.
So now we have to solve for A, B, and C.
A, B, and C, and Ati and Hitchin have done that. Okay, so there's explicit answer now, just in terms of hypergeometric functions. So completely, we've finished the problem. But I'm not going to write down the full answer, I'm just going to tell you a little bit about it.
And they depend only on smaller.
They depend only on small r. That is needed from SU2 invariance. Anything that depends on angles would not be an SU2 invariant. Why is that? Because scalar functions from our analysis of spherical harmonics transformed in j comma j. So there's a unique scalar function that is SU2 invariant, namely j, namely the constant. Okay? So the only way we're going to get SU2 invariance is 2 things. A, that we make it out of right invariant one forms, and B, the coefficient functions of that are not functions of angle at all. Only of radius. Is this clear? So that's the point. The point, I should have emphasized this more. The point is that this is quite remarkable. Let me emphasize this. If I told you that our metric was SO3 invariant, you would have said, good, that has reduced our problem to ordinary differential equations. Because SO3 invariance completely determines angular dependence. Has to be, the angular dependence is that of the round metric on this way. And all unknowns are in radial dependence. That's the problem of ordinary differential equations. Now I'm telling you much less. I'm telling you the problem has only SU2 invariance, half of the SO SO4 invariance. Still, that is enough to completely reduce the problem to ordinary differential equations. Because there is no function on the sphere apart from the constant that is invariant under even one of the 2 SU2s.
No scalar.
There's, no scalar function. There are scalar one forms,
Which
but they're only a finite number. So the coefficients have to be functions only of r. Cannot be functions of the angles. This is clear? So this SU2 invariance, just like SO4 invariance, was enough to reduce the problem to ordinary differential equations. The price you pay is that you have ordinary differential equations for more functions. For SO3 invariance, we would have had sigma 1 square plus sigma 2 square plus sigma 3 square and one overall function outside. And then by choice of radial coordinate, we could have made it a problem with just one function. Okay? Here we have to deal with 3 functions. That is the price we have to pay because we have less symmetry. But the price is not such a big one because we still deal with ordinary differential equations. That's a huge thing. Partial differential equations are hell on earth. Ordinary differential equations are civilized objects, right? So, okay. So, fine. And, okay. Now there are 2 things that I want to tell you about this. About this metric. First, when we go to asymptotic infinity, okay? When we go to asymptotic infinity, Okay. This metric reduces to the following. Okay. When we go to asymptotic infinity, this metric reduces to the following. These are all constants. These are the constants we had in previous lectures. G is the coupling constant. Theory M was the mass of a monopole. Okay, these are all constants. Divided by 1 by u of r into d chi plus omega dot d. Okay, I'm going to tell you a little bit more about what this is. Where omega is the magnetic is the potential for a magnetic monopole. So omega obeys the equation del cross omega is equal to r hat by r square.
Is there a square in the second?
Yes, thank you. What? That the solution for M4 at infinity reduces to this. In a particular coordinate, a convenient coordinate system reduces to this.
U of r is
U of r is some function that goes to 1 at infinity.
goes to 1.
Goes to 1 at infinity. Okay? So now let's look. So at infinity we just in our mind set U of r to 1 and look at this object. Okay. This object has the following. For a moment, set omega to 0. In fact, omega is 0 at large r, locally, because field strength dies off like 1 by r. So locally, omega is 0. Okay, so then what is this metric? U is 1. This is some number, it's the radius. You see, this is the metric on R3 times S1. With a particular radius for the S1. Fine. Okay? Now we've kept one correction to this large R behavior because it's very important. And this one correction goes as follows. You see, along with that d chi, we have omega dot dr. Now, what is this doing? Maybe some of you have experience with Kaluza-Klein theory. You know, so when we look at Kaluza-Klein theory, we look at a space which is where there's some xi coordinates and let's say a theta coordinate. Okay? And then we write down a general metric but with d theta plus ai, the whole thing square. Now, this ai, do you know what I'm talking about? Let me write it more clearly. We write down the most general metric. Exactly. dxi, dxj, okay, plus e to the power phi, or maybe sometimes people write 2 phi, d theta plus ai, the whole thing square. You can always put any metric in this form. Okay? And then you notice that if we want to preserve invariance under, motion in this theta direction, then the kind of diffeomorphisms were restricted to our xi mixes up with xi is a function of xi, or theta goes to theta plus a function of xi. But under such a transformation, theta goes to theta plus a function of xi, ai transforms in order that this not change. AI transforms exactly like a gauge transformation under U1 gauge field. Okay? So in Kaluza-Klein theory, when we take this form, we identify AI as the gauge field. The quantity that transforms under U1, under the U1 gauge field that we get from Kaluza-Klein reduction. as a gauge field. Now compare that to what I written down above. Chi is my theta, and omega dot dr is my A. So what I'm saying is that we've got this R4 times S1, but in the presence of a Kaluza-Klein gauge field. And the Kaluza-Klein gauge field is what? It's the Kaluza-Klein gauge field of a magnetic monopole. So this is a space that has the topology of what is called a Kaluza-Klein monopole. Okay? Under the Kaluza-Klein gauge field, from Kaluza-Klein reduction on this S1, what we have is a gauge field in this problem. And this gauge field carries a monopole charge. Okay? That is the, in two monopole moduli space, this comes out. Okay? So, at infinity, the precise metric doesn't stay this all the way. Okay? At infinity, this space looks like this. Is this clear? Okay? That's the first thing to know about the space. Second thing to know about this space is that there is one point on this space where one of these functions, that I think we can choose it as A, or maybe they've chosen B. Let me look. A, where one of these functions goes to 0. Now you see, if you've got a one-form field going to 0, the coefficient of one form going to 0 in a metric, you have to be careful. Because that could be a place where your metric develops a singularity. So for instance, suppose we take R4 in double polar coordinates. Okay? So that we have the two planes, and the radius and angle in the two planes are R1 theta 1, R2 theta 2. The metric for R4 is dr square is equal to dr1 squared plus R1 squared d theta 1 squared plus dr2 squared plus R2 squared d theta 2 squared. This is clearly fine, even though the coefficient of this one form goes to 0 at R1 equals 0, and this one form goes to 0 at R2 equals 0. This is a nice smooth manifold. However, if I change this to half, then it's no longer smooth. You will have conical deficit at R2 equals 0. Right? So places where coefficients of these of smooth, well-defined one-form fields go to 0 are places of potential singularities. But they needn't be singular. Okay? But the lack of singularity, is not generic. Generically it will be singular, but needn't be singular. So now, in this metric up there is a place here in the choice of coordinates where I set this f equals minus b by r. That place happens at r is equal to pi. It doesn't matter. That's convention. That's some convention of what that coordinate is. Okay? At r equals pi, there is a place where a becomes 0. But the whole metric is tuned so that that location is not singular. It's smooth there. Okay? But your coordinate system goes funny there. Just like polar coordinates go funny at R1 equals 0. Okay? So the two places you have to be careful, at which you have to be careful, the two places where you have to be careful are r equals pi and r equals infinity. What do you have to be careful about? Okay, so far we've just done some geometry. Any questions about the geometry? Now we turn to the physics, and then we'll see what we have to be careful.
The metric that you wrote at large R,
yes.
Why is this R equal?
So I am sorry. I have now talked about the full metric. The thing with the hypergeometric functions that we've not talked about. Okay, this is r equals pi.
It's about f of r, a r, and a of r, and b of r.
It's about a of r. At r equals pi, a of r goes to 0.
Okay, that is a full metric.
The full metric.
Okay.
Yeah.
This is the one that's valid
Only at large r. Okay? Yeah, you see that this, this metric as anyway, fine. Right, the full metric is much more complicated. This metric is very simple, there are no hypergeometric functions here. Full metric is hypergeometric functions. Okay, good. But the important thing is that there are two places where you will need to give human attention, One is r equals pi, the other is r equals infinity. Now, human attention for what? Okay, now let's get back to physics. Remember that what we wanted to do was to check whether at every odd value of the charge, at every odd value of the charge, there was a bound state in this problem. That was what we're trying to do. Okay. Now, we've a supersymmetric bound state, right? Okay, but you remember what a supersymmetric bound state was? It was a harmonic form. However, it's got to be a bound state, not two particles moving away from each other. What does that mean? It means it has to be normalizable. Which means under the usual norm for forms, it has to integrate to, it has to be normalizable on this M form manifold. It doesn't have to be normalizable on R3 times S1, because even a single particle is in a plane wave on R3 times S1. But there should be no further divergence in the norm, because that would be like a two particle divergence. We want to see that there's one particle. So we are ignoring the R3 times S1 totally, on which it will be a constant. Okay? In the relative coordinates, it should be normalized. It should be a bound state. Okay? So that is the first thing. Second, duality demands that there is exactly one such state. Because there was exactly one W boson.
For one odd charge.
For one particular charge.
Okay.
But now you see, we have a bit of a puzzle. Because suppose we got a one form. Now we've got this four-dimensional space. So state is some form. We don't know what the dimensionality of that form is. Could be one form. Suppose we manage to find this a normalizable one form, which is harmonic. Now it's a simple mathematical fact that if you've got a harmonic one form that is normalizable, its Hodge dual, which is a three form, is also harmonic and also normalizable. But as a state, it's different. So it looks like we always have states in pairs. So it might seem impossible for duality to be correct, unless we have a two form and it is self-dual.
Okay.
So why should it only be one?
One, because the number of W bosons, the prediction for these states came from duality orbits. And we're looking at duality orbits of W bosons. And we have only one W boson. So we know exactly how many it should be. Okay? So, if this works at all, we have to have a two form and it has to be a self-dual. Now, one can write down, right. What Ashok did was, went as follows.
So the aim is to show that there are no one form or satisfy this.
First, that there are none of those.
And then
That there is exactly one normalizable two form.
we should show both of them.
We should show both. Now, Ashok, I don't think I haven't looked at his paper of late, but what he didn't show, what for sure he showed was that there existed exactly one normalizable two form. Okay, but by now I'm sure everything has been shown. Okay, okay. Okay. So we want. Okay. Now there's one more thing. Remember that this Z2 action that we talked about at the beginning. Okay, that Z2 action could be thought of as moving in one of the two S1s. Okay, so this Z2 action is moving like in one of the two S1s, and since we expect this form to exist only for odd charges, this thing should, under this Z2 action, which is 2 pi rotation under one of the two Z1s, one of the two S1s, this thing should be odd under that Z2.
Where are these two S1s?
Go to infinity. We've got these two monopoles, each of which have their own S1s. Remember that the Z2 came by 2 pi rotations under one of the two S1s, but not the other one.
2 pi?
2 pi under one of the two S1s, which translated into pi for center of mass and pi for relative.
Okay.
Okay? So now we do the Z2 action. That will continue to be pi for center of mass. But it will be whatever the Z2 symmetry is on this Atiyah-Hitchin manifold. This Atiyah-Hitchin manifold comes with a Z2 symmetry. It's one of the things they impose and they show. Okay? So this form, whatever it is that we write down, has to be odd under the Z2 action.
At infinity, is chi going to pi plus pi?
Yes, at infinity, chi goes to chi plus pi. Exactly. And is whatever that becomes in the full manifold. Okay? And what? Because we expect dions in the two monopole moduli space only with odd electric charge. Charge is related to this motion. You remember we expected it only with odd electric charge because we acted with ABCD, this SL2Z transformation on 1, 0. But ABCD, and we got the charge AD minus BC. But the co-prime business. You remember that, right? Right. So, putting all these conditions in, Ashok was able to show that he wanted a 2 form. It had to be self-dual, had to be odd under this S1, this Z2, and he was able to basically to argue that the form that we are looking for must take the following structure. What? This is capital F of R times these things are what appeared in the metric. Having all these here was needed for it to be self-dual. Okay? And this is what we had.
So those are only sigma ones.
The only sigma ones. You can write this, of course, in terms of sigma 2 as well, because d sigma 1 involves sigma 2 and sigma 3.
Right.
Okay? But this is a compact convenient form. This is d sigma 1, and one can easily check that this is self-dual, and Ashok had some arguments that this was the most general, physically reasonable self-dual form. Okay, so self-duality already has bought us a lot. Now we need harmonicity. It's got to be a harmonic form. The fact that this is harmonic gives you some differential equation. In fact, it gives you the differential equation del f by df by dr is equal to minus fa by bcf. Okay, it gives you this differential equation. All these are known functions. That came in the Atiyah-Hitchin metric. What is unknown is this capital F. Now this is a linear differential equation which can always be solved. Okay? Solving it actually is hell on earth, because there are hypergeometric functions, but we don't care about the actual solution. We just want to know whether the solution exists and is unique. Okay? So now we start at r equals pi. And then the fact that the solution is regular there, despite this coordinate system breaking down, tells us how the solution must go there. Then we integrate that solution out to infinity and check whether it's normalizable. Okay, going through this exercise gives you the answer yes, then obviously it's unique because we've put in every condition. Well behaved at r equals pi and then integrate out to infinity. So there were two conditions. These two conditions look like they could conflict with each other. Right? You take an arbitrary differential equation, put one of these conditions okay, but because there's just one, it's just linear, order one differential equation. So you can put one condition, but we had two physical conditions. Okay? Nonetheless, you put one of them in, check the other one, turns out to be true. Okay? This was the check that Ashok did to verify this prediction of duality for the existence of these bound states. Okay? Any questions or comments about this?
So harmonic condition meaning you have a second differential equation and you integrate.
Yes, except that it's already self-dual. Okay? So the harmonic condition is like d star.
Yeah.
So one of them goes away. Okay?
So it's only a first order.
Yeah, it's only a first order kind of equation. Okay? So, fine. I haven't gone through all the algebra here. But I hope I've outlined the...
Is this there in Harvey's notes?
No. The more algebra is not there. Ashok, of course, goes through the algebra in his paper. And if you want details of the Atiyah-Hitchin metric, for instance, I could send you some references. Yeah. Harvey's notes has a little more than I've told you about, but not much. Not much more. But of course, he has references.
You taught this from Harvey's notes?
I've taught, almost all of my discussion was from Harvey's notes. Okay? Yeah. So, I suppose that's because when Harvey's notes came out, I was trying to learn this stuff. I found the notes very useful as a student. Okay. Excellent. So, fine. So I think, apart from questions and comments, for now at least, we will stop our discussion of four-dimensional supersymmetric theories. We've had some discussion of n equals 1 theories, some discussion of n equals 2 theories, some discussion of branes, and some discussion of the n equals 4 theory. Would have been fun to do a little more about the n equals 2 theories, these Gayotto things. But let's postpone it. It's taking forever. Let's move on. Maybe we can come back.
How do you say that at r equal to pi is regular?
No, now this isn't just a local differential equation. Now you have to impose what it means for the solution to be regular at r equals pi. Meaning you go to r equals pi, transform to regular coordinates, demand that f is regular in those regular coordinates, transform back to your coordinate system, and see what that means. You understand what I'm saying, right? So, for instance, in polar coordinates, if we had a gauge field, a theta has to go to 0 at r equals 0, like at least like r, in order to be regular. If it just went to a constant, it's not regular. So you can't just take the function and demand regularity because we're in a bad coordinate system. The safe way is to go to a coordinate transfer. Go to a good coordinate system. See what it becomes and read that off. Okay. So whatever condition that is what's imposed on f. That gives you one condition. Now you integrate. There's no further
So
freedom.
No, now you go to a new regular coordinate system and integrate there.
No. You work in this coordinate system. You solve this differential equation. It's like, I don't even know what the condition is, but let's say that r equals pi. Your condition is that it has to go like r minus pi cube times an arbitrary function.
Okay.
You put that in. So near r equals pi, it goes like r minus pi cube.
And then solve.
Then solve the equation.
Okay.
Okay? Then it is what it is. Okay. And you get what you get, and it's either normalizable or not.
The fact is to find that form, that r minus pi
Cube.
whatever.
Yeah. That is, of course, a very simple exercise. Logically, you know what to do, right? This is not a hard thing. It's like we do in polar coordinates. Okay. Excellent. Any other questions or comments?